So in this video, I'll discuss how to identify a chiral center. And so a chiral center is simply a tetrahedral carbon that has 4 different groups. So recall, in order for a carbon to be considered tetrahedral, that carbon has to have 4 bonds around it. So in this case, it has to have 4 single bonds around it in order for it to have a tetrahedral geometry or a tetrahedral shape. If it has a double or a triple bond, it no longer represents a tetrahedral geometry, so therefore it cannot be a chiral center. Also, by saying 4 different groups, that doesn't mean the atoms directly attached, but this entire group that is attached, all 4 must be different. So basically you're starting at that carbon and you're working your way to the end of the molecule in all 4 directions. So let's say we had the following compound. So I'm just going to draw out the actual Lewis structure so you can see all of the bonds that are present. You see all the atoms that are present. And so we have this compound. So if we go from left to right, and if I number those carbon atoms, this will be carbon 1, 2, 3, and carbon 4. So if I look at carbon 1, so carbon 1 will be the carbon that I'm looking at, I'm interested in. It's tetrahedral because it has 4 bonds around it. However, those groups that are present, the group to the left is just that hydrogen, the group above is just a hydrogen, the group below is just a hydrogen, but then the group to the right would represent all of this. So in this case, carbon 1 has 2 different groups attached, so carbon 1 would not be a chiral center. So again, in order for it to be chiral, all 4 of those groups would have to be different. So carbon 1 is not chiral. We can do the same thing with carbon 2. So since I drew on it, I'll redraw this molecule. I have my 4 carbon atoms. Carbon 1 had 3 hydrogen. Carbon 2 had a chlorine and a hydrogen. Carbon 3 had 2 hydrogen. Carbon 4 had 3 hydrogen. So now we can move on to the next carbon, carbon 2. So now if I look at that one, I have my group to the left, which in this case is all of this. So all of that is one group. I have my group above, which in this case is just a chlorine. I have my group to the right, which is this CH2, CH3 group. And then I have my group down below, which is simply a hydrogen. So all 4 of these groups are different. So because all 4 of these groups are different, carbon 2 would be a chiral center. So we can go through that process with the remaining carbon atoms as well. However, simply looking at carbons 3 and 4, I can see that they each have multiple hydrogen atoms attached. So what that tells me is that carbon 3 cannot be chiral, carbon 4 cannot be chiral. So this particular molecule has only one chiral center, which is at carbon 2. Having a chiral center means that this molecule can exist in 2 different 3D arrangements. You may have it where the chlorine is coming towards you. You may have it where the chlorine is going away from you. So there are 2 different ways in which this molecule can be shown. So if I were to go and draw this same compound in a skeletal form, so what we typically see would be 1, 2, 3, 4, and my chlorine was on carbon 2. And recall, because this is a skeletal structure, I don't actually see those hydrogen atoms that are bonded to carbons 1, 2, 3, and 4. They're present, but they are not shown. However, knowing that we have a chiral center means that I can now indicate the 3-dimensional arrangement. So what that means is that I can indicate that that chlorine is either coming towards me, and so I can show that as a solid wedge, meaning that the hydrogen will be going away, or it could have been the opposite way. It could have been that the chlorine was going away and the hydrogen was coming towards me. So having a chiral center means that there are different stereoisomers that I can obtain. And recall, a stereoisomer simply means that we have the same molecular formula, so the same type and number of atoms present. However, although they are connected the same, so in other words, they have the same 4 groups, the arrangement of those groups are different. And so carbon 2 is our chiral center. In both molecules, it has the same 4 arrangements, or excuse me, the same 4 groups. So that CH3 group, so we see that to the left. That Cl, we can see that. That hydrogen, we see that. That CH2, CH3, we see that. So each one shows the same 4 groups, but the arrangement of those groups are different. In the molecule to the left, there's chlorine because it's on the solid wedge. The solid wedge means that it's coming towards you. When you see the dashed wedge, it means that it's going away from you. And so the molecule to the left, that chlorine is coming towards you, that hydrogen is going away from you. But it's the exact opposite in that second molecule. So although these both look like the same molecule, they're different versions of stereoisomers. And so looking for your chiral center will allow you to determine whether or not different forms or different types of stereoisomers can exist. If no chiral center is present, the molecule is going to be identical, so you would only have one form. So we'll do another one. So let's look at this compound. So my recommendation, my bond is a little off. That should be on that carbon. My recommendation, when you're looking at a molecule, see if you can eliminate any carbon atoms that could not possibly be a chiral center. Right away, I see a double bond. So I know I can eliminate those carbon atoms because this is not a tetrahedral carbon. In order for it to be tetrahedral, it has to have single bonds. Even though we have a skeletal structure, wherever you see a single bond, that means that there are hydrogen atoms that we do not see. So even though we don't see all 4 bonds, they are present. However, that double bond no longer represents a tetrahedral geometry. So right away, I can eliminate any double or triple bonds that are present. Another thing that we can eliminate, we can look at hydrogen atoms. So I know this carbon, I only see 1 bond. I know carbon always has 4 bonds. Because I only see 1, that means that there are 3 hydrogen that I do not see. Because there are more than one of the same group, I know that that carbon cannot be a chiral center. So I can do the same thing with this top carbon because it also has 3 hydrogen. This top carbon also has 3 hydrogen. This carbon all the way to the right also has 3 hydrogen. So all of these carbon atoms are eliminated. They cannot be chiral centers because they have more than one of the same group. So that means that we can look at these remaining carbon atoms. And so this particular molecule would be numbered left to right. So that would be carbon 1, 2, 3, 4, 5, and 6. So if we were to look at carbon 4, so I'll redraw this molecule. So if we're looking at this carbon, carbon 4, I have to identify my groups. I can see that carbon 4 has 2 bonds. So what that means is that I have 2 hydrogen. So really, I don't have to go any further. Since there are 2 hydrogen, I have 2 of the same groups. Even though I have this group to the left and I have this group to the right, I have 2 hydrogen. So carbon 4 cannot be a chiral center. Let's look at carbon 5. So if I were to redraw it again. So now we're looking at carbon 5. I can see that carbon 5 has 3 bonds. So that means there's 1 bond we don't see, which is the hydrogen. So we have that one group. We have this group to the left, which is a methyl group. We have this group above, which is also a methyl group. And then we have this group to the right. So in this case, because we have 2 methyl groups, again, this is not a chiral molecule. So none of the carbon atoms in this compound are chiral. So what that means is that this molecule can only exist as one stereoisomer. And that is if we're simply referring to those in enantiomers and diastereomers, or looking at mirror images. That's what that chiral center allows us to determine. It allows us to see that we have molecules that have the same formula, the same connectivity, but a different three-dimensional arrangement. So let's do the same thing looking at a ring, so a cyclic compound. So if we were dealing with a ring, we have to determine whether or not chiral centers can exist in a ring. So let's say I had this compound. So if I had this compound, so right away I would go through and eliminate carbon atoms, because I know that this top carbon has 2 hydrogen, the upper left carbon has 2 hydrogen, the bottom left, the bottom middle, the bottom right, all of those have 2 hydrogen. So none of those carbon atoms could be chiral. So that leaves us with 1 to test. So the carbon where this functional group is located, I can see that it has 3 bonds, so that means there's 1 bond that's missing. So we're missing a hydrogen. So if I were to redraw this compound and show that OH and show that hydrogen, so now I have some different groups. So still focusing on this actual carbon, because we have to look at carbon atoms. This is one group, that OH. This is one group, that hydrogen. So we can see those 2 groups, but what we're left with from there is simply this ring. And so when you're dealing with the ring, the way you treat the ring will determine whether or not it is one group or whether or not it is counted as 2. So you have to start at that carbon that you're interested in, and then you're working your way around that molecule in both directions. So starting at that carbon, I have to go to the left, so counterclockwise, and I have to go to the right, clockwise, to see if I can determine the difference between those carbon atoms. So for this, I'm going to just jump back over to this structure since I have the number of hydrogen written. So starting at that carbon, I work my way around in both directions. The next 2 carbon atoms are both CH2, so they're both identical. So then you have to keep moving. So then I move to the next 2 carbon atoms. Again, they're both CH2, so they're both identical. So I have to keep moving. But when I move this time, now I meet up at that same carbon. Because I could not determine a difference between these carbon atoms before they met up, this would not be a chiral center. So this is not a chiral center. The reason why is because now, since we met up before we can determine a difference, that ring simply counts as one group. So that means that this carbon only had 3 groups around instead of 4. And so therefore it would not be a chiral center. But let's see what would happen if we had that same compound with that OH. But let's say we had a methyl somewhere. Say we had a methyl over here. Now we can go through and do the same thing. We already know that we can eliminate carbon atoms because this still has 2 hydrogen. This bottom left still has 2, the bottom middle, as well as the bottom right, they each have 2 hydrogen. So we can eliminate all 4 of those carbon. That leaves us with that top left and that top right. So let's say we want to do that top right again. So I'm going to redraw it and actually show the OH and the hydrogen. So again, we can see that this is one group. This is one group. I left that methyl off, sorry. And from there, we have to do the same thing. We have to go around the ring to determine whether or not the ring counts as 1 or 2 groups. So this time when we go around the ring, so we're still looking at this carbon atom. So I'm going to jump back over to the structure that shows the hydrogen. When we look, so starting here, working your way around, these are the first 2 carbon. They're both CH2. They're both identical. So we can't determine the difference, so we have to keep moving. So then we get the next 2 carbon atoms. They are different. One, this top left only has 1 hydrogen, and it has a methyl. This bottom middle has 2 hydrogen. So there are 2 different carbon. Because they are 2 different carbon, we can treat this ring as 2 different groups. So it's almost as if we're saying this ring is going to split because we can determine the difference. So as a result, we're saying, okay, we have this group and we also have this group. Because they are different, this carbon would be a chiral center. We can turn around and do the same thing with that top left carbon where that methyl group was located. So now starting at that carbon, working our way around the ring. Again, we're going to work our way around in both directions. So when we do that, now we're starting here, first 2 carbon atoms. So if we're starting here, first 2 carbon would be the bottom left and the top middle. They're both the same. One is a CH2, the other is a CH2. So they're both identical. So then we have to move to the next 2. I have a CH2 and then I have a CH that has an OH. So because of that, we can treat the ring as 2 different groups. So we have, again, we're imagining that this group or this ring is split to allow us to count it as 2. So we have this bottom group, we have this top group. We also have our methyl, and what I didn't show, we had 1, 2, 3 bonds. We also know that there was a hydrogen present. So that means that we have our methyl group and we have our hydrogen. So this carbon also has 4 different groups, so therefore it is also a chiral center. So this molecule has 2 chiral centers. So we can determine chiral centers in molecules that are acyclic, meaning that they are chained to carbon atoms. We can determine it in molecules that are cyclic, meaning that they have rings of carbon atoms. And so regardless of which type of structure, you want to make sure you're looking for tetrahedral carbons, so carbon atoms that only have single bonds, and all 4 groups must be different. Doesn't mean that the atoms directly attached have to be different, but the entire group. So for instance here, this carbon, I can see 3 bonds. I know there's a hydrogen. This is a carbon. This is a carbon. This is a carbon. So it has 3 carbon atoms directly attached, but we have to look at the group. So starting at that carbon, work your way to the end in all 4 directions. To the left, you would have this. To the right, you would have this. Down below, you would have this and that. All 4 would be different. If it helps you to name each group, do so. Think about what a substituent that has 1, 2 carbon atoms would be called. We would call that ethyl. What would a substituent that has 3 carbon atoms be called? It would be propyl. Here we can see that it's just hydrogen. And if we have a substituent that only has 1 carbon, it would be methyl. So we can see that there are 4 different groups because we have 4 different names. So this is how you determine chiral centers. I hope that this helps. If not, feel free to reach out. Thank you.